Hi everyone. In the previous lectures, we began with our discussion on conventional and double sideband amplitude modulation. We then said that to save bandwidth, we can do a single sideband suppressed carrier modulation. And before we go to see how a SSB signal is generated, I'll first lay the mathematical foundations necessary to better follow that content. One such idea is the Hilbert filter. The Hilbert filter, we will later see, is very useful in generating the SSB modulated signals. The impulse response of a Hilbert filter is given by 1 by pi t. The frequency response of a Hilbert filter, which is the Fourier transform of 1 by pi t, is minus j signum of f. I've already discussed how did we get this result in one of the previous lectures on Fourier transform. We began with the Fourier transform of u of t, then we found out the Fourier transform of u of minus t, and from that we derived the Fourier transform of signum of t, which happened to be 1 by j pi f. From that, we used the property of duality in Fourier transforms, and we derived the Fourier transform of 1 by pi t to be minus j signum of f. So, a Hilbert filter, looking at it in frequency domain, it multiplies all the positive frequencies by minus j and all the negative frequencies by plus j. So minus j is simply e power minus, it's a complex number, so we can write it in Euler's form, so it will be e power minus j pi by 2. So if I take a positive frequency sinusoid of frequency f, I can simply multiply the frequency response evaluated at that frequency. So this is from the simple theory of frequency response. So since it's a single frequency sinusoid, I can simply do that. I can multiply it with the Fourier transform evaluated at the frequency of interest. And here it's same for all positive frequencies, so I'll write it as e power minus j pi by 2. And immediately you can see the output of this Hilbert filter will be the same complex sinusoid phase shifted by pi by 2 radians. And we can similarly show if I feed a sinusoid of frequency minus f, you will again see the same phase shift of minus pi by 2. Okay, so since it's a negative frequency sinusoid complex exponential, I'm multiplying it with e power plus j pi by 2. So you'll again get a phase shift of, if you take minus j common out, you would get minus pi by 2 as the phase shift. So Hilbert transform, a filter, can also be seen as a minus pi by 2 phase shifter. The magnitude here, if you take the magnitude of this, absolute value of this, it's 1 for all frequencies. So which means the magnitude response, if the input contains certain frequencies with amplitudes and magnitudes of certain values, that remains unchanged as it passes through the Hilbert filter. The only thing that changes is the phase. Here, for example, if I feed any sinusoid of frequency f, for example, if I feed cos omega ct, the output of a Hilbert filter will be minus pi by 2, you will end up getting sin omega ct. So because it's a minus pi by 2 phase shifter, we can directly see this here. We will now look at a few more properties of the Hilbert filter. So for example, if I pass a signal x of f through a Hilbert filter, so let's assume this x of f is x of t is a real signal, then the Fourier transform will exhibit conjugate symmetry. So if you consider two frequencies f and minus f, the Fourier transform at these 2 points will form a complex conjugate pair. Once I pass it through the Hilbert filter, all positive frequencies are multiplied by minus j, negative frequencies are multiplied by plus j. So if you see, again the conjugate symmetry holds. So which means if I pass a real signal through a Hilbert filter, the output will also be a real signal. Okay, and that should sound obvious because you're convolving it with the input with a real function 1 by pi t. So therefore output should also be real. So at the output you should expect the Fourier transform should show conjugate symmetry. Now what happens if x of t is real and even? If x of t is real and even, if we can look at this function itself, the Fourier transform is going to be real and even as well. It's going to be real and even. So the Fourier transform, when you multiply it with the minus j signum of f, you can immediately see the Fourier transform is going to be purely imaginary, and again it's going to exhibit odd symmetry because it's a real signal. So therefore, the moment it's purely imaginary and odd symmetric around f equal to 0, we know from the properties of Fourier transform an odd signal obeys this property. you can easily see y of 0. Y of 0 is simply the whole area under the Fourier transform, so which is nothing but integral of y of f df will be equal to 0. So y of 0 for an odd signal, this condition has to hold true. Y of 0 has to be equal to 0. Okay, so that condition holds true. So if you pass a real and even signal as an input to the Hilbert filter, output is going to be an odd function. Similarly, if I feed a real and odd function, if x of t happens to be real and odd, then the Fourier transform will be purely imaginary. And again, it should exhibit conjugate symmetry. So if I multiply it with, say, let's assume if this was j, this is going to be minus j. Okay. Now, if I'm going to multiply this with minus j signum of f, for all positive frequencies, it's going to be j square is minus 1 into minus 1, you will get plus 1. And for negative frequencies, it's again going to be minus j into minus j, which will again be minus 1. So it will be a real and even function. Okay, so your Fourier transform y of f is going to be real and even. So which means x of y of t will also be real and even. In a few moments, we will see that if you pass a function, a signal x of t through a Hilbert filter, the output y of t will be orthogonal to the input x of t. Therefore, if x of t is real and even, y of t has to be real and odd, because for them to obey the condition for orthogonality, that will naturally follow as a consequence. The next property is, what about the energy at the output? What will be the energy of y of t if you pass as energy or power at the output of this Hilbert filter? How does it change? How does it affect it? Now, one thing intuitively we can see, none of the magnitude energy from Parseval's theorem, we can directly see that energy is simply given by mod of x of f the whole square df. So from this, we can directly see, since the magnitude function remains unaffected, the energy should remain unaffected. So if you see the magnitude mod of h of f, the Hilbert filter's response is 1, mod of y of f will be equal to mod of x of f. So therefore, the energy at the output should be the same as energy at the input. So energy or power at the output will be same as energy or power at the input. So energy and power is conserved. So output power will be equal to the input power. Again, it can be very easily shown mathematically. So y of f, mod of y of f is simply equal to mod of x of f, because the magnitude of the Hilbert filter is just 1. Now, another important property is what happens when you cascade Hilbert filters. What happens if you cascade more than one Hilbert filter? So we saw, you can see a single Hilbert filter as a minus pi by 2 phase shifter. If I cascade 2 Hilbert filters, so that will be minus pi by 2 and minus pi by 2, you get minus pi. So it's simply, you can easily show, multiply the frequency responses of the 2 Hilbert filters, minus j signum of f into minus j signum of f, you will end up getting minus 1. So the output of 2 Hilbert filters will be minus of x of t. So if you cascade even number of Hilbert filters, you will either get plus or minus x of t. You will either get the same input as if you cascade 4, you will get plus x of t. If you cascade 6, you will end up getting minus. Okay, so you will either get plus or minus the input signal as it is. The next property is orthogonality. What about y of t and x of t? Will they have any correlation present? Will there be any correlation between y of t and x of t? If you pass a signal x of t through a Hilbert filter, we can easily show, I'll show it in a few moments, that the output and input will be orthogonal to each other. Now, one can readily see, we are multiplying the Fourier transform. If, for example, I said one quick test to see whether they're orthogonal or not is that you should be able to represent y of t in terms of x of t, some scaled version of x of t. Okay, so here for orthogonal signals, this condition will not hold true. So that is, the inner product of x of t and y of t will be 0, and that result can be readily shown by performing this integral and using one of the results, one of the properties of Fourier transforms which I had already used. If you have two functions x1, x2 dt, if you perform this integral, that will simply be equal to x1 of f into x2 of minus f df. Okay, so with that we can readily show x of f is the input function, the input Fourier transform. Y of minus f is x of f times y of f is x of f times minus j signum of f. So y of minus f will be x of minus f into minus j signum of f, a signum of minus f. Now if you remember, for a real signal, x of minus f is simply x conjugate of f because they obey the conjugate symmetry property. So we can directly write the integral as x of f into x conjugate of f into minus j signum of minus f can be simply written as j into signum of f. Okay, so minus j signum of f, you just have to reflect this function around the origin. So you will get a function like this. So it will be plus j minus j, it will be simply j into signum of f. Now this function mod of x of, what we are going to do is that we are going to multiply this with mod of x of f the whole square into j signum of f df. Now we know mod of x of f for a real signal will be an even function. We are multiplying that with an odd function j signum of f, so the integral will be 0. And this is something we expected previously as well. When we were seeing if you fed an even signal, we were getting an odd signal at the output. So the inner product of an even and odd function is going to be 0 anyways. Okay, so that's it. So these are some important properties of the Hilbert filter. The next lectures, we'll start developing a few more mathematical ideas and eventually start our discussion on single sideband modulations. Thank you.